Oh yeah, now it's okay.
Yeah. So I'll share my desktop.
Okay, let's make you our introduction first. So let's start. Let's not don't wait. So welcome to join us on this online meetup. This is our first meetup we organized in this year, and actually this is the first formal online meeting we ever had. And today we are going to have a seminar of introduction of Libra and blockchain. Before we start, as we always did, right? I will give you a short introduction of Toronto Big Data Professionals Association. I know all members and most people already know our organization, but I still give a short introduction to these who don't know, right? Toronto Big Data Professional Association was founded in 2016. So it's a non-profit organization that focuses on big data technology in financial industry. So basically, our mission of this organization is, cooperate with professionals in the industry to promote and advance big data technology, provide a platform for big data professionals to share and exchange experience and ideas, right? So we organize roundtable discussion and seminar of new technology on regular basis. But this year is very special, right? This year because the pandemic, we really don't have organized any meetup in this year. This is our first meetup actually. So actually, if you are interested to join our organization, you can visit our website www.tolantobigdata.org, right? If you're really interested, you can visit our website and join us. Because today we have more than 40 people registered for this event, the traffic could be high. So please unmute unless you ask a question or it's your turn to speak. And today we invited Mr. Qin Wenyan give us our introduction of Libra and blockchain database. Mr. Qin is an expert of database development. He is also a pioneer in the blockchain and digital currency. He is the founder and the president of North American Blockchain Foundation, Canada, initiator of Open Libra framework, Velas.io, and founder of Canadian Digital Asset Exchange Company. So let's welcome Mr. Chen to give us this presentation.
Yeah, okay. So I'm so happy to present here in the Toronto Big Data Professional Association. So basically, I had done an introduction for the blockchain, I think last year for this organization. So this time, I'll be more focused on the database because under the hood, right? It's not the blockchain is already is more popular. People already know the basic idea and how it's going to use. I think the biggest application is the Bitcoin digital currency itself, right? And then especially now, many of the government, the countries, the central bank already implement and come into a solution with the central bank digital currency. Maybe in China or not, but we know that the China now is not yet blockchain. That's their target. They are going to implement the blockchain in the future. I think that's in their plan. But basically, what happened here in the most advanced the blockchain based digital currency is that now coming is a Libra. Libra now is a Libra association, is initiated by the Facebook. But Libra, the reason why the Libra is so important is that Libra blockchain now is the most advanced the blockchain technology, one of it, right? beside the Bitcoin, Ethereum, Fabric, IBM had a Fabric, right? And Hyperledger, and many of the Hyperledger the systems. And now we have the Libra database, okay? And in terms of application, right? Libra actually target the financial infrastructure. They're saying that I'm doing the database, I'm doing a different systems. And then now they are binding to the different currency. The original Libra idea is that they're bonding a bucket of the currency, just like IMF, right? International Monetary Foundation, right? The bucket of the currency. Now, after they back and forth doing the compliance, we know that last time we know that Bitcoin cannot be compliant, regulated by any of the governments, but things are changed, right? So why not we cannot be compliant? That's why the Libra, okay, I want to do the compliance in the government by government. The first one, number one, is the US government. So it's going to bind directly one-on-one with the US dollar. As the spread of the Libra and the Facebook application, so many people, right? Billions of the Facebook users, as long as they're using the Libra as their, and for example, Libra payment system, right? They're going to do a Libra payment system. And then the Libra database is sit behind this. That's why it's so critical and so important, because we are all have the financial and banking background, right? We all know that, right? So all the financial system behind it, it doesn't matter is the exchange, stock market, banking, or insurance, whatever, the money market, foreign exchange, underneath are all stand for a database. And then what is a stand for this, the future digital currency about the US dollar, or maybe the Chinese RMB and Euro, all this currency, what is sitting behind this is the blockchain database now, right? Even that's why it's so important. We go into this, what sitting behind? Why not the DB2? Why not Oracle? Right? Why not the big data? Like we all know that the not long ago, like it's a Snowflake, right? A big data platform. There is a good, very big IPO, right? So now that's why today we are coming here. We're figuring out the under the hook, what is behind this blockchain database, and why not, and what's the difference between the RDBMS and the big data not secure, and why we need this blockchain database, and why not Bitcoin, all those kind of things. So we're going to, actually this is pure technical. I hope you will understand some of the very basic database concepts, and then also some of the software component architectural things. And then and also I'm going to try to do a live demo at the end. Live demo is that I'm going to get the source code from the official release. Now it's the version 1.0, right? And then I compile it from the source code and run a local database, and create a transaction, and then create an account, and then mine the coin, and then initiate a transaction, and then ask the people, Alice, to send certain a transaction to a certain asset to Bob. This is kind of a live demo. I'll try to go through that. Okay. Yeah, let's get started. So I think it's everybody here, right? Yeah, let's get started. I don't expect too many people, right? It's us. I expect the right people. Okay. So basically, the blockchain database. At the end, I'll go open up some of the Q&A, the questions. So basically, the blockchain database is that now the reason why we have the blockchain database is that we need to meet the challenge about the distributed computing, because in our traditional way of the handling the system cannot meet the requirement of that. The reason is that, so the first thing that we need to get a definition about a blockchain database. Blockchain database is a cryptographically authenticate. It's not different from the previously like centralized, because authentication is based on the cryptographics, right? But it's still a distributed, right? You need to have a different signature, right? And then it's a single version, because across the universe, one blockchain only has one version of the data. Cannot be a multiple. Even you are the multiple copy, but you are still a multiple copy of one version. This is really is a key concept. So it's compared to difference, because the reason I'll explain later on. And it records at the public ledger. It's a public database, which means that whoever has the client are able to access it. And the permission control is very loose. It's not tight, right? For the traditional database, the DBA actually is the king of the database. It can do anything. But now even the client, it will be, because it's public available to the society, right? And that's why. But the transaction is the ledger behind all this kind of the system. It's public available to everybody. So the design, right? And this is all the transaction has been executed and shared to all. We call it the client is that it's not the certified client is losing. It's anybody. So which means that all the participants, you will be able to access this ledger and the transaction and then the data. Okay. So the reason is that we all know that, right? Previously, right, the client server, we had one single server, and later on we scaled, right, to meet the business requirement, the growing up, and then we have to come up with the clustering, right? Clustering, and then later on clustering, how many clusters you can host it. But now we had, for example, we had 10,000 of the nodes. And then how can we handle those kind of situation? And then we come up with we need to meet this kind of the challenge. But if we saying that every node, since the node is untrusted, it's public available. For example, we had the DB2. Not everybody are able to access the DB2. In the application layer, it's the application server has the database backend. It's the certain account access the database. But now if it's a database open to the public, how are we able to meet this kind of the distributed and mass request application, right? This is the challenge about the database. So that's the reason is the blockchain database is a solution for this kind of challenge. That's why I'm coming up with the concept is that don't get people wrong, right? The blockchain is meeting this kind of requirement. So the mass access, different role are able to access the transaction. I want a transaction. I want to know, and I want the transaction cannot be, it's mutable, right? Cannot be changed, and then it's trusted. That's the kind of things. The first thing is the communication. As the number of the node grows, we have a challenge. So when the system is growing, like it's different system has different computation model, right? The communication mechanism between the system is already changed. The inter-process, for example, the DB2, you cannot TD Bank's DB2, you cannot access the RBC DB2, right? Directly in terms of, I don't mean that the authentication things, right? We need to that kind of things, especially we need to have not the client server anymore. We will need a broadcasting things, and then the network model is changed. Otherwise, so huge amount of the nodes cannot be well communicate. So we had a history, right? We had a PC to PC, right? And then we had a client server. This is environment, right? Environment is that's why I call it distributed database and distributed computing is involved. One machine to two machines communicate together, multiple machines communicate together. We need to have a model. Client server model is that, look, we had a server in the central, right? and then all the clients. After the nodes, number of nodes grows, we cannot meet that certain requirement. The performance goes down. We cannot have the availability. And then we need to have a certain network model. And we come up with the different model, right? We need to have the cascaded, federated, different model. I think so this. Okay, I need to, yeah. And then this is kind of the distributed model, network model, and a different model. At the end, we had another model called peer-to-peer model. This is more like an internet. So that's like every computer is connected to each other, but we are not trusted. Why not 100% available or not always online? This is the traditional way of the client server, the communication network model might not meet the future requirement, right? So that's why the second challenge about this is that the fault tolerance. Because as the number of the nodes grows, there will be always a certain number of the node going to fail. And then maybe certain, so we already know, we have been already met this scenario many times in our real industry and application. For example, certain server fail, everything, the whole system is going down or something like that, right? And we need to have a certain mechanism to prevent that certain key nodes or key about the failure. Or maybe even some nodes actually sending out the false information, right? If one single, and then that's why we need the fault tolerant things. The fault tolerance in the client server, the traditional database is that we use a two-phase commit. It's one coordinated is asking, okay, I'm going to commit, everybody is ready, everybody come to me. That's called the centralized system, right? You come to me and go, okay, everybody saying yes, and then I commit, and you just do the replicate. That's the reason why is that our traditional way of the database is doing this way. The reason why I think from the 1970s, and then all the system, financial system are still using the RDBMS, the database. It's because of this transaction. And it's going to allow this kind of fault tolerance is that any other client are able to fail to get the wrong data. So the server is sending out everything. So the server is coming up. And in terms of the analytic things, right? As we growing up, somebody is not, okay, I don't want 100% transaction things, but I just want to know some of the data. And then they have come up with different, as the number of the nodes grow, they come up with a different protocol to make sure the data integrity. So for example, this is run 3PC. We had a two-phase commit, and then later on we had a three-phase commit, and then we come up with the different idea, the federation. IBM even had a federation, which means that, for example, federation three-phase commit, or many of these kind of the way is kind of the database protocol. Behind the scene, they are doing the fault tolerant. They maintain the data integrity. Yeah. And the third the challenge about is the decision making. The parallelism, as long as the number of the nodes in our distributed system, right, grows, and then how to make a one decision making is a challenge. For example, 10,000 of the nodes. How can we make one decision making Alice has $100? Everybody has agreed with that, and then sometimes it's a very complex and computational problem, and we need to have all the nodes combined together to fix one problem. And then the way is the decision making, and then we have the transaction. We need to have the transaction management. Yeah, that's why we have to break it down into our computing task into different pieces and send to the different across the network, and then collecting back the result, and then make Alice has $100. Alice had $100 has to be divided into different tasks by the different computer. When they calculate, they had collecting the result. And what kind of the logic behind that to making the result? And then we need to make it's not availability, not just availability. We need to make certain result, and it's a consensus to Okay, yeah, yeah. This kind of will involve in transaction management. So the transaction management, now we are going to into the 3 categories. Now it's the secure transaction management. NoSQL. NoSQL also has certain transaction, the data integrity. Right? We had a consensus. Here is one of the case that we divide. And then one of the decision making is the algorithm is the BFT, called Byzantine Fault Tolerant. It's model ones is the protocol as the main the certain agreed for a certain data. That's that the blockchain database actually is meet these 3 requirements. It's not the same anymore, right? So let's go back to see traditional way of the RDBMS. RDBMS is also the same. It's JAP, right? A client asking send a request to a server. The server getting the request based on the language the client is sending to us. For example, RDBMS is a secure. They communicate with the server is the secure statement saying that I want to do certain things, manipulation for certain data. And then all the server have their own protocol, have their own way to handle the data. DB2 has this, it's all behind the scene, it's the database protocol. So many people doesn't realize that. But now the reason why I highlight this is because the protocol become important. Because previously, if the one single node, the protocol is executed in the one single machine, it's okay. It's the one single machine's responsibility to make sure the data is integrated. But if we cross the node, and across the node is not centralized, especially you don't have the central master server. Anybody is a master. Anybody is the client. Anybody, some of the key nodes are equal. We know that. And then how are you able to make sure the data availability, the data integrity, and the data security, and the performance as well? And then we can see that the traditional RDBMS, they also has the database protocol. They talk to different each other and then they communicate, make sure. DB2, the very famous one, is open group, right? It's open as well, right? It's open public. It's the called DRDA database protocol. I was working in IBM lab. I was in the DRDA team. That's why I know very well about this database protocol things. And Oracle has its own database protocol. They implement a different way to handle the data availability. For example, you ask me for data, I'll give you the data. You delete the aggregate or whatever, do a join, or maybe the subset, querying, delete, or something, CRUD, right? Update the data. They have the mechanism to handle. Postgres also has at the beginning, Postgres doesn't have a protocol. Later on, they say, okay, we need to come up with an idea called protocol. They call it front end and back end protocol. Right? The SQL Server, either it's a Microsoft SQL Server or Site-based SQL Server, they also use one database protocol called tabular data stream. They tell me, for example, it's a machine-to-machine communication. You send me a 00 binary things. How do I know what you're talking about? What kind of data you request? Underneath is all this database protocol. So the client requests the data, the server get the request, compile whatever the language they communicate, and then dump it, going down to the different components. You can see that the different database server, they handle it differently. And then, I think, sorry, this is, I think I make a mistake here. The DB2 is not this one. DB2 is not this one. I think I made a mistake. I will have the DB2 one. Yeah, the DB2 is different. This is in the middle is the still. It's the DB2. Yeah, it's the DB2. Yeah, it's the DB2 architecture. I got it from the IBM. It's not I drew it. Okay. Okay. So that's the single server. For example, in terms of the number of the nodes scaling out, I use a case of an example about Oracle had a rack. DB2, I think the DB2, right? They has the evolution things. One is in the left-hand side is that the DB2 single node. On the top is this one here is the DB2, the data partition. Data partition. And the bottom one is the pure scale, right? Pure scale. And then very beginning, our architectural design from the sheer nothing, because everything is in one server. The memory, disk, like CPU are all in one server. And then later on, we want to, one single server cannot be handled, as I mentioned in previously, right? The only way you can, for this single server things, you can only scale up, which means you have to add that more storage, memory, and then giving a powerful CPU. But if you want to cross nodes, and then you need to have come up with technology. The first thing is the data partition things, right? Data partition things. And then the second one is the sheer nothing, sheer everything. Data partition is sheer nothing, which because each node has its own memory, CPU, and then the storage. And for the sheer everything is that, for example, the IBM Pure Scale or maybe Oracle Rack, is that you need to have the sheer disk. And also some of the sheer memory, right? The CPU can also has a clustering of the CPU. That's like the way that people want to become making the system more powerful. But there's a limit. There's a limit, or there's also a certain scenario we need it. Now it's very powerful in terms of performance. The pure scale things is really super power already, right? We are able to handle that, right? But there is a certain way. When we are building the cluster, there is a certain way that we are able to handle that database distributed system differently, which means that we are a supercomputer. We are sending out the CPU, memory, data. They are all hosting in different host machine. But actually, the different group of the machines parts, they are actually unified. For example, as I mentioned that, right? The CPU, there are 10 sets of the CPU and doing one task. And the other set of the CPU, they're doing the one task. Eventually, they aggregate the result together. And this kind of the system is imaginable. Right? We are trying to build this. But how can we maintain the data integrity? The reason here is that the client is sending a request to the server. The server using their own way to manage the data and then aggregate and then send back to the client. So how about this? The internet, more like an internet database. This is the data in different machine. The memory are in different machine. How are we able to separate the task and spread the network and later on aggregate the result back? And then we still have a certain agreed for the data and not we had a good communication, right? Availability and also the false tolerance, so that the system is not down and you are not getting me the false information, and you need to still maintain the data integrity. And also the ACID, we know that the database is called ACID, like called atomic consistency, isolation, and durability. This is kind of the traditional need for the data RDBMS. What can we still do that? For example, in the blockchain way, like the storage might be spread and different. Anybody, if you want to donate your storage, you just hook it up your machine, and then your machine is part of the network. You are doing the computing. We already know that many of the experiments have been done. That, for example, I remember a long time ago has a task using the share your Linux. And then you install a host that, and then Linux is going to automatically run certain computing problem, solve the certain problem, later on aggregate. That's the idea. Come up with the peer-to-peer network. The computing network it becomes to a peer-to-peer, or maybe a fully distributed. It's not just like our certain interest of the centralized. And by this one, we need a database. That's the basic requirement about a blockchain database. And the blockchain database, not necessarily to think about it is a Bitcoin. Bitcoin is just one of the blockchain database that use the specific database protocol. Just like Oracle is using the TNS, right, called Transportation Network Structure. DB2 is using the DRDA, right? And Microsoft SQL Server is using the TSD, right? And then Bitcoin is using what kind of database, the protocol to maintain its data? We call POW. It doesn't matter is mining or not. I don't care about that's another economist, right? For example, the reason why is mining is that you take a reward is that at the very beginning, the Satoshi don't know who is going to run this machine. He's going to get a war. So people are joining this one, right? And then there is also another protocol, proof of the stake. Proof of stake is that you have the vote. For example, when you're making a decision about a distributed computing, we need a decision making. The decision making is based on the people had the right to vote, which means that you had a stake. And then you're able, for example, I had a 10% of share. When I vote, I make a contribution for the 10% of the decision making about certain data integrity, right? That's one of the POS. POS, very famous POS, the protocol is by the implemented by the Ethereum. Ethereum is the POS, right? Yeah. And also the other way of making the decision is that the BFT. BFT stand for Byzantine Force Torrent. That's kind of algorithm. This kind of very famous one blockchain database is the IBM Fabric. IBM Hyperledger Fabric is the practical force torrent. I'm going to give a detailed explanation. And the Libra database, he come up with on top of the certain BFT called Hotstart. Hotstart, and he's going to do the improvement. They come up with their own BFT called Libra BFT. By this kind of database consensus, we call it database protocol. We are able to make the future database. This is called blockchain database. It is because the reason why is that because the database blockchain database protocol is so important. The difference of the protocol actually make the difference about the database itself. The people are changing the database protocol by meeting certain requirements. For example, the Bitcoin's the POW protocol is meeting the electric payment, preventing double spending. That's kind of thing. I have done a previous lecture saying mentioned a lot about the POW, how to handle the double spending, maintain the data integrity, right? And the Ethereum, I don't want to talk about that now. And the fourth Byzantine Fabric, IBM Fabric is very popular. And then we are focusing on the Libra BFT. Okay, so here is that the distributed database. I think I call it because it's the first time I'm saying that the blockchain database. I think not that many people are talking about this, right? I want to get a full picture, an overall picture about the blockchain, where the blockchain database is stand in our architecture and then system design, the diagram, right? The client, okay, we come up with a distributed system. In the middle one, we have the RDBMS and cluster. We mainly using for transaction, online transaction processing. So focusing on the transaction. Also, the RDBMS also has the tuning so that you can tune to a OLAP and OLTP. We also have the DBA to tune that, right? Because most of the time you're hosting the data. The reason why is that because it's a relational database, relational data. They have the entity and relation, those kind of joining, different foreign key, those kind of data structure. And then because it's a high data integrity and maintain the ACID, it's also force tolerant because the server, the master server actually control everything. And then it has a balanced performance. For example, if you are a single server, you get high value, high performance. If you want to scale out, scale up, and then you get very high performance. And scale up, as long as you want to maintain the centralized, the master database, you still have the very high performance. And later on, we had, okay, sometimes some of the situation, for example, as long as I have this huge amount of the data, I want, is 80% of people agree with something, is already no. I already enough for me to get, I don't need the 100% of the people agree with certain data. And then by that one, the NoSQL, the big data is coming into being, is that he sacrificed the data integrity. He sacrificed the ACID to get certain performance. His goal, the OLAP is for the analytic only. I don't want 100% tiny little things to be maintained. I just want to know the likelihood, or so that by that way, but I need high performance. I need growing up, it scale up. And I also, I need to handle the non-structured data. I don't need structured data at this time. I don't need to maintain the relationship about this data. That's why we come up with the NoSQL, right? And how about the other side? As long as the node is growing, do we have the solution to, while we are growing, scaling out the system, growing up the number of the node, we still be able to maintain the strong data consistency? Yes. That's where the blockchain database is coming into being. And at the end, I'm going to also give you something, maybe my vision about future database might come in. It might be a mix, just like the RDBMS, the OLTP and OLAP are mixed together. The blockchain database and the RDBMS are able to mix together as well. And even three of them are mixed in certain giant system. For example, the central bank, the cryptocurrency, they are all mixed. I believe that. So, and really importantly is that the blockchain database, they maintain one single database, single version, because everywhere you go, as long even you are a separate system, you are in your file work, like behind your organization, but your database has to be a single version. That's why. And I still maintain the performance, right? The Bitcoin performance is another issue, right? But there's a certain things we still able to maintain. That's why. This is the extreme case. This is the peer-to-peer, the Bitcoin network. Bitcoin network is a system. Believe it or not, it's inevitable, right? You cannot deny that. Bitcoin is a database. It maintains, Alice has 10 Bitcoin. That kind of the data integrity across the world, across the different nodes. Even the nodes are not trusted each other. He still are able to maintain. It's ACID, it's the atomic, right? It's the consistency, it's isolated, it's the durability. It maintains a strong data integrity. But now Bitcoin's performance is not that good, right? We know that, but is there any solution? Yes, we have, right? Right? The Libra is that this is distributed. We might not exactly be centralized or pure peer-to-peer. And then by this way, this is the network, I think, in the future. You don't come up with the extreme case. Oh, Bitcoin is you think about the blockchain is only the Bitcoin case. No, it's a mix. Everything is mixed together because people, different systems, they meet the requirement of the different purposes, right? Here is that. So we have a network, we have a cluster, certain system might connect to the RDBMS, NoSQL, and then they had, for example, the transaction, stock exchange, market money, money market exchange, and then they have own storage, and also they have their own smart contract repository. Here is in the right-hand side, there's a smart contract repository, right? And that's the future about the use case, use scenario in the of the blockchain database. So the blockchain database will be combined. Remember, no long ago, when the NoSQL is coming up, everybody, okay, NoSQL is going to replace the SQL. No, that's not the case, right? It's a NoSQL in RDBMS, the harmony is coexist together very well. That's the same case for the the blockchain database. The blockchain database is going to coexist with the existing legacy system very well. So as we are the system, right? People, we cannot give a false statement to the application, the business side, saying that actually it's a mix, right? It's a hybrid. Okay. That's previously we get overview about where the blockchain database is stand for and what's the relationship between the RDBMS and the big data and why we call it a blockchain database. And we already know that. I think I'm sure that people previously listened to that till now understand this kind of case. So rest of the case, I'm going to get into the detail about the way about the Libra. You know, so many blockchain database. I only focus on Libra because it's so important, right? Libra is the same. So you can see that in this diagram. The top one is the official from the Libra website. Is that I join as another one is a client is sending a request to a system. The system is called a validator, right? We call it validator. Every node is you don't have a master. You in the Libra database is all peer-to-peer. So every node is equal. Every node is equal for now. Yeah. So all you can get is when you download the source code, you have the validator, and then you also have a client. Now the client actually is built together. You also have a client. The client can be separate, right? The client, when you're using a client, you can request to the validator. One validator is one master. If the two validator is the master combined with the two validator, like this is and then the validator actually actually there is a leader. It doesn't matter where you get the request. We can always have the load balancing to routing the request to a certain leader. The leader has your request is going to send out to the rest of the validator. This is the protocol. The one in the box in the text box is a protocol. The complexity the system is handling the client's request. At the end, the client, the server has to be getting back the request, the result, the number 5 to the client. And then number 2 is that when a leader gets a request, he's sending out to the rest of the validator. The validator is going to do a consensus. They based on their own storage, based on their own validation, based on their own capability. Because each validator, they are independent. Not like our traditional RDBMS cluster. Everyone has to be controlled by the admin. Here is no admin, right? Each node can be acted single independently. But we also have a consensus, the way how you joining the network, that's another story, not in the algorithm level, right? And then after each node, they're doing their own regulation, execution, consensus. They agree with a certain request. Everybody agrees with that the system getting a result is aggregated by a leader and returned back to the client. It's still the same. It's still the same. And then you can see that the data integrity about this blockchain database is increased from the right-hand side to the left-hand side. Because NoSQL is the very weak data integrity. SQL Server is the same, had a high data integrity, but the blockchain is a strong data integrity. In terms of the scale out, blockchain database and the NoSQL scale out, the number of the nodes is can be grow without a boundary, right? Without the limitation. But the scale out of the RDBMS has a limit. I'm the person actually done that in IBM. Actually, when I was in IBM lab, I built up a 128 DB2 nodes as a cluster. That is the theoretical limit. Theoretical limit still has a 256. But I built a 128 nodes, physical nodes, when I was in the lab. That is already some of the many limit. Nowadays, there's very few system. They had a case about this, the 128 nodes, DB2 nodes, right? So, but in Facebook, they had to build maybe 10,000 of the 30,000 of the MySQL cluster. That's another case. So the database about the Libra is still the same. we have asking the database protocol to give us the result. That's still the same, right? It's the database protocol control things. So underneath about the database protocol, I give the we call it Byzantine fault tolerant overview, right? So we know that underlying the blockchain is all Byzantine fault tolerant. It's all about the consensus. They call it consensus protocol. BFT is one of it, right? So we all know that, right? When there is very ancient so algorithm problem, right? You can have a lot of the reference online, but I just give a very quick case. For example, Lucas from the #1 general, it sent out the consensus to all the other generals, and the generals talk to each other, and then later on they sync the votes. And then, for example, if there's a 2 general, actually it's a traitor, and then we still have the 5 lawyer general, and we are able to make it. The algorithm, the research already come up with a conclusion that the number of the nodes compete, right, with the number of the false node, because of the traitor is this kind of equation, has to be greater than the 3f plus 1, which means that, for example, in this case, we are not able to actually has the perfect fault tolerant. Because the reason why is 3f, I can just give you a quick my understanding, right? For example, you need to get rid of the traitor. For example, you have the n number of the n. So first thing, you need to get rid of the number of the traitor. Even the reason why is that, for example, now here is the #2 and #4 is the traitor general. But when in the real system, we don't know. The worst case that we get rid of the 2, there are 2 honest, loyal general become unavailable, shut down, the server is shutting down. So the case is that we can see that we get rid of this 2 good general, this n minus 4, minus f is 1. And after that, so we had only 3 good general, and then the 2 traitor. They had to sending out the communication. They had for example, you need to have the quorum. You need to have enough legitimate vote, and then you still need to get rid of the legitimate vote. For example, you need to get rid of the 2 worst case scenario, so that you get rid of the other 2 of the good general, the worst case, right? And the case you have the 2 traitor and the 1 lawyer, and at the end if they vote, and then the system will be compromised. So that's why this diagram is not meet the requirement about the fault tolerant one. The number of the nodes needed. For example, here case we have the 2. We have the 2. We have the 2 traitor, and the number need is that we need the 7, and still we able to handle this. Okay. Oh yes, now it's 7. Yes, we are able to handle it. That at the end there is because the end vote is the 3 lawyer general vote against the 2 traitor, and then we still maintain the system integrity, right? So okay, here we come up with the Libra. What's the difference? What's the change about the Libra? What's the difference? That between that's they are the BFT voting things. They're voting things, right? The voting things is that they come up with at the very beginning. Right? So this is a different 4 phrase. We are not 2 phrase commit anymore, right? We had multiple phase of commit, right? This is the extension about to meet the requirement about the challenge about the distributed system, right? So it takes long. So it goes more than long, different long, and each round the leader is chosen among the validator. For example, we had 7 people, 7 generals, 7 nodes. We pick 1 node as a leader, and then the leader aggregate They sending out the leader proposed. Okay, so we have the one person has a transaction. He initiated a block of transaction and broadcasting to rest of the to rest of the validator. So for example, here is the leader. He's getting a transaction, a block, it's broadcasting to all the generals. All the generals a validator, and Libra is co-validator. The leader also need to collect enough votes. This enough vote is that called N minus F, which means that it's legit. There is the legitimate the vote to get the we call a column certification in the Libra called QC. The column is that you need to have the legit vote. For example, here nodes is the 7, the fourth the nodes is 2. So we need to have the collect. You need to collect at least the 5 votes and make your transaction become legit. The leader then broadcasts the column, which means that you have a certain vote, 5 votes, at least the 5 votes. You get collect all the votes, broadcasting to the validator, and each validator certified, because for example, you need to have the 5, and certify at least 5 column we call it column certificate, and then commit in your local server. Your local has the local storage into your local storage, and then you commit it, and then later on become a next round. Every leader, in case of the leader actually fail, for example, there always one leader is always we don't know that if the leader is a fail in this cell, right? For example, leader is down, right? Or maybe the leader cannot aggregate enough votes. For example, the column is a 5 votes. He cannot collect enough 5 votes, so he had to step down. Then he has to time out this round. Time out this round, we will come up with a new round, because we always need to have the available nodes to become a leader. A leader will be chosen again. So it has that's one. But within the transaction, we still split into the 4 phases. We call it prepare, pre-prepare, pre-commit phase, and then a commit phase, and decide phase. This is kind of the different machine, right? They have to come up with these kind of things, right? This come with, for example, here is a node, right? The node 3 is the leader, right? The B, we call it the block. V, we call it vote. C, we call it column, the certificates. And then leader is a 3. He collected and sent out to the rest of the node. He collect a vote. And all the nodes vote back to node 3. After node 3 get all the votes, it commit, the column commit to the rest of the nodes. And then round by round, right? Different round, right? The round 2, the leader become node 0. So you can see that the different round is that the node become the leader become the node 1. The reason why is that, as I mentioned, keep them in mind, force tolerance. In our traditional way, master cannot be done. That's the key things we already know that. For example, master database is down, the whole network shut down. By this way, no master. Everybody is the leader. We pick a leader, and the leader down, and the other one become the leader. This becomes the high availability, because a system we cannot be trusted. Each other might not be fully trusted each other. We cannot say that who is the master? No, and no master. And even certain things we had a master, when master down, we still are able to provide a service. The system still need to be available, right? That's the Libra, the BFT, and then I'll come up with that later. Right? You can see that the Libra BFT inside the validator, right? So you had a picture, right? We had a 3,000 high level. Now we get into the component. We come up with the consensus protocol. We come up with the internal about the validator, about this one node. This is the diagram, the logic about one node. The one node, the client still come up with inside the node validator. It has the administration control, admission control. With that, they're going to do authentication, verification. Who is this client? does he has is legit to do the system access? What kind of resource they are able to access? Once the admission control has it, it send out request and he send out the resource to the virtual machine. He's not making the decision. He's only collect the information. After the collect the information, he's not decided. He sent to the virtual machine. It's the virtual machine to do the decided. After then, he sent it to the virtual machine and he sent to the memory pool. And also he sent it to the storage, the admission, the component. And the memory pool has to maintain all the data. So this memory pool goes, okay, I'm going to send it to the virtual machine to make sure that this data can be run in the virtual machine. It's the virtual machine to decide it. It's because this virtual machine is not controlled by certain admin. Because these need to be communicated. It sends out the communication, the number 5, to the other validator. The other validator is coming up. So there's a multiple. For example, we had 100 validator outside. We need to send out to the 100. We're broadcasting it to the validator. And the validator is the number 7 coming back. Coming back to a certain node, because all the validators are equal. They do the consensus based on the protocol. The consensus protocol is number 6. Number 6, after they have the protocol, the consensus they send to the memory pool. The memory pool also connected with the virtual machine. And then they send to do the execution. After we had to come out with a consensus, they are not making the decision. It's the virtual machine. The virtual machine is more like a judge. It's a black box judge, just like a US Supreme Court, right? As long as I have the certain things, I'm not sure, right? I don't make the decision. I send to the virtual machine. You give me the result about all these kind of things to maintain the data and the system security. At the end, all this they come up with after they had it, the execution also send back your local consensus also send back. Now your local result. Sorry. Your local result also sent back to the consensus and communicate with the other validator. So the consensus is the key component. Also the virtual machine. The virtual machine is that the SQL, only SQL, the bytecode. It's not it's encrypted by bytecode, binary code, like to maintain the data security.
Sorry, I have one question here, right?
Yeah.
Is the storage. So in this case, did all the validator have to have a copy of the data? Because if you want to validate, you have to have the data to validate. In this case, did everyone have to keep our same copy of all the data, or is just some people keep, each validator or only keep some part of the data?
Good question. Now, yeah. Well, this is a good question, right? The reason why is that in the Bitcoin is more advanced, the blockchain database. Bitcoin is separate. It's in the light node and the full node. The full node contains all the full set about the database. Light node is also only use the crypto, the encryption data as long as they maintain the it's a subset of the header of the certain data for requesting. Only the full node are able to make the consensus. Yeah, right. So now the Libra is maintain the full set of the data. But I think if it's an enterprise level of the Libra, for example, some of the Libra they only handle the payment, right? The payment system, right? They have a buffer of the payment. The local they are able to handle it. The line nodes. Now there is no line node of Libra yet. They're all equal for validator. We call it validator. And then you are right. As growth, right? As the number of the data grows, they will meet this kind of the challenge. And then I think that's why I come up with a solution at the end. You are a good question, right? And then in terms of the storage, I'm going to use the RDBMS to store all the data and then still maintain the data integrity. Yeah.
Okay.
Yeah, now the Libra is the full set of the data. Your good question. And in the next slide, we're gonna what kind of data we store, right? Right? It's still a storage, right? The consensus, after the consensus, we still need to know what kind of data we install, right? Okay, here. So here is that the data is transaction. We call it the Libra data is, for example, blockchain database is maintain what kind of data? It's transaction data. It maintains the transaction history, right? It maintains the state. For example, every time, every moment of the time, there's called state. Here is a triangle one, is the S. There's a state of this database. Okay, for example, today, 2020, 11/06, certain time, there's a state about this Libra database. And then if certain one transaction happening, if there's a new transaction, the state will change. Libra database is maintaining this kind of transaction change state. So that's the key things. It doesn't matter if it's a relational or not, right? It's a key value or not. The main purpose is he maintain the transaction history. And also it's a single, every node has to be the same version without assumption. Or because later on the data will be by the consensus, because internally, right? As we mentioned, right? Internally, the data, the storage is controlled by the consensus. Even your local, you are not control the data. It's only everybody make the consensus before you can dump it to the storage, right? So that's why even you make a force, you hack your own system. As long as you hook up, the consensus is going to getting back the right result of the data. Otherwise, okay, you fail. You are not able to. You are made next time before you can want to do something, you need to sync up with the data, and then you need to keep the state. So, for example, you need to keep a state. For example, number 100 state of the database, and then a Libra database keep these two data. It's a state. The other one is keep the transaction, and then we can see that a transaction is, for example, the state is the Alice. Let's make a. And then the state is a function of the previous state and the transaction itself. Here is F, is a function. I call it F, is a function here, right? Is that so each state has to be from the previous state. And then with new transaction coming in, the state change. And then the state history and the transaction state history change. For example, here is that let's look at the state n-1. Right, the previous state. The previous state is that Alice has the balance for 110 Libra coin. Bob had the 52 coin. And the transaction is going to that Alice is going to send 10 coin from Alice to Bob. The TN is the transaction itself, right? TN is the number N transaction. Is that the transaction is sending a coin from one the account to the other account. Execution, the component execution is doing this kind of execution. The state N will become, after the transaction, the state N, the new state will become, the balance Alice is 100, but we have the 62. So we have this kind of things, right? And then the function is the deterministic function. We know that is the automata things, right? It's that this function that is always the same, the finite state. Right? You had the initial state and initial state, right? It's a finite automata, right? We know that, right? This is the Libra blockchain as maintainers. They are different from the Bitcoin, Ethereum are different. The Libra is simple. The why the Libra is so powerful, and I think it is more advanced blockchain database is very simple. It keeps the state, and and Bitcoin is a UTSO, right? We know that UTSO. I'm not going into that detail, but the Libra is that maintain. I want to only maintain this, but the transaction is that you can holding is a coin, but you can holding information too, right? It's a different state. We can use the state, right? That's the here we will know a transaction state, and then later on we will come up with this how we organize this transaction. How are we organize this state, and what kind of data structure actually is using, right? Okay, that will be later, right? We continue to come up with the full picture. Let's get the full picture about the system architecture, about the Libra. Libra is the, sorry, this is not life cycle, it's the system architecture. Libra has the consensus component, memory pool component, peer manager, networking provider, and connectivity manager. For example, the network provider is that, so they come up with the different the inbound and outbound message. And then you're going to check the discovery, the chain, and then check the health check, the connectivity. And also they have the remote procedure call. They call the remote procedure directory, and they also have the direct connect. Direct send is that you already send a low level, it's a faster, trusted nodes. They can directly send, and also has a peers. And all Libra is using a called actor programming model, which means that all the components are receive a task sent by we call a task router. Here is we use asynchronous computing framework. We call it Tokyo. Tokyo is asynchronous, more like a message queue, right? If you are doing everybody get a request, you come up with a message queue, either Kafka or maybe MQ, they're sending out to the different subcomponent. The subcomponent is this network protocol peers, and this is the system architect. Okay, this one is the storage. That's why we come up with a storage. The storage has a storage wheel, storage client. They use the protocol and the service. They use a Merkle tree. They handle the Merkle tree. Underline, they have their own schema. The different schema, because the data they connected together, they need to have a schema. At the end, they have the Libra DB. Libra DB actually is on top of the Rock DB. I can tell you, right? It's on top of the Rock DB. Rock DB, we all know that is a key value things. We will be able to use the level DB as well, right? It's we know that level DB is the Facebook's the key value, and then the DB is categorized in different set. It's called ledger set, state set, transaction set. This is a key value. Right hand side here, I call it enterprise extension. It's my idea. I think that we know that if the database, right, different nodes, they are and might belong in our real case. For example, the RBC is the blue one, right? The orange one is the TD Bank. No, maybe CIBC. The green one is the TD Bank. They have their own data, but if they are going to do the consensus, just as assumption, right? Right? But the RBC's data, TD Bank's data, or CIBC's data, they can be hosted in the same rack. The reason why the Bitcoin is that they have to cross the geography, right? Cross the remote side. But if they are in the same rack to do the consensus, will be much more easier, faster. Because they are in the same rack, in the same location. You sync your data locally, right? But if you have the trusted data, for example, the rack 1 is in downtown Toronto, rack 2 is in the Barrie, right? Rack 3 is in New York City, right? But internally, you can use your faster track, your trusted replication across the geography, right? Is that geolocation, right? You can do a very quickly synchronization, but you do a local consensus, you can do in the local rack. That's why once you get into the enterprise level about the future blockchain database, you need to come up with this kind of hibernate. And each one, the data, because the RDBMS, I use it as a solo purposes. I only solo purposes is to sync from the Libra database. By this way, the availability and performance will have a huge amount of improvement, right? because we already have the bottlenecks now in Ethereum, Bitcoin as well, but they don't have the solution. Vitalik has a solution. Or can you do a data shedding? Data shedding is what kind of the solution? Data shedding is this kind of solution for IBM. You can see that, right? We have that one, data shedding here, right? Data shedding is just the DPF for the DB2. But we have the better performance is the pure skill. We should share everything, right? But that one we will be able to handle more cases in terms of performance, right? That's why that's the idea I'm coming up.
Well, actually, I have one question here. Do you mean that the different bank data of a different bank are in the same database?
Yeah.
Well, do you think this is possible? I don't think that's really possible.
Yes, they will be.
Trust each other,
They will be. Really... They will be. No. That's the case. For example, now the Chinese central bank, Chinese digital currency, right? Central bank digital currency, right? All the bank has to be in the same database. Even you still have your own database. That's coming to that reality now. That is now, right? So even, for example, the Canadian central bank, right? They come up with the crypto central bank currency. They have been tested using the Ethereum, right? They has to all the bank has to be in the setting up a database. Assume it's an Ethereum, or maybe assume it's a Libra. I think they are testing the Libra very soon. Otherwise, we are going to give them testing
actually,
Libra.
In this case, actually, you create a center, right? You create a data center that everyone can trust. It's not really, in this case, it's not really decentralized as a blockchain database. It's more centralized because in this database, you hold all the data for everyone. Right?
Yeah, but it's not controlled by everyone. There's no central admin. I understand what you are thinking, right? I understand what you are thinking. Just like you remember RDBMS, right? A database, right? You have a master slave, right? You have one master, 100 of the slave, right? The slave is the replica, right? That's why you mentioned that. But the reason why the master control everything, the slave is not controlled. But here, slave is not a slave. Slave can become a master as well. It's not we call it the DRDA things, right? It's not the slave is going to promote as a master. The reason why it's promoted to a master is still need the master to control. Here, there is no master. That's why, but no master, still one single version database. This is one concept. Yeah.
No, I think there's another question probably. So you're basically each node will have all the data.
Yes.
Think about the volume. It will be huge.
Yes. That's what happening in Bitcoin.
But you are a relational database here.
No.
Yeah, I think Bitcoin
the
probably.
Relation database, I use relational database as the event of persistent storage.
Yeah, I think the question is about. Right? Yeah, I think the question is about the storage.
For example, your DBA here, right? You change your RDBMS, your organization, but later on the Libra database still have it. You have to sync it. Why you change it? You create trouble for your own organization. For example, if all the 100 other banks are saying that Alice has $100, only the TD Bank is saying that Alice has $0. It doesn't make sense because the TD Bank's DBA doing that change, it doesn't make sense. You understand? You have to make it back. Alice has $100. You'll be forced to do that, right? No. That's my idea, right? We don't know. In the future, there might be something.
I'm not really sure. This really, this attention part is not really. I'm not sure it really makes sense. But anyway, we can continue.
Yeah, that's my proposal, right? My idea, right? Okay. So underneath the data, right? the data is that let's continue to get right the ledger, state, transaction, and what's in that data. What's the difference between compared to the RDBMS and then the NoSQL, right? The data is this. It's that you call it Spark Merkle tree. Well, Merkle tree, we know that right, is also using the hash function, right? Every node is using hash function to make sure that there are there's no it's mutable, right? And then he maintained the ledger history, right? You can see that he maintained the ledger history. It has the validator, the signature data is also in this. Also, it maintained the ledger state, and it also has the ledger state. We call it ledger state. We also already know that because the Libra database is a transactional the state of the state. It keeps the list history, and each version is represented by a Spark tree. Spark tree is a different version. This is the Merkle tree actually maintained is the version. Now, your good question is that now Libra is maintaining the whole set. The whole tree is stored into the data, into the dumping persistent serialized into the data. It is serialized using the key value, and also has the event, at least the event. By this ledger info, it has the version. What version you are? For example, you are in the state n or n-1 or this kind of things. And then transaction accumulator is a hash. Actually, it's kind of maintain this kind of and rest of the information. And it's also some of the consensus data are also stored in the ledger info. And ledger info, when you get into the leaf, right, you will have a transaction. T4 here is a transaction. The leaf, the transaction data actually always stored in the leaf. And the leaf actually maintain a link to another called state. It has the root. The root actually maintain all the state. The state, and at the end of the state has the account info, and also has the event. So what happening to this? And then there is another Merkle tree. This is the data structure, and this Libra is dumping all this data into using the schema and then dumping into the storage. They call it rock DB into a key value things. Right? This is the okay. Let's come up with the some of the concepts still come back. Let's come back. We see that the transaction and what the database is doing, and where is the consensus, and then what's the data, and then there you come. Libra has an account. How Libra is organized, since it doesn't have the administration, no DBA, and what is the account? How are people are going to do it? So the transaction here is that the people Libra transaction is that it has a maintains an address, key, the gas, the information, like the signature, and then the signature number, and then also some bytecode. It has the reason here is the transaction maintain a bytecode is the move program. Move programming actually it has the whole complexity in this transaction. It's the move that maintain the all the consensus. Move are able to programmable. The move is an address. It's an address because the Libra is the resource programming. It has the different address, has the different resource. For example, Alice has an address. This address can bind, has a certain of the move programming binding to this address, to this account. A certain address has the move, and the move can be programmable. It's a binary code. When just like our SQL in our RDBMS, what kind of the vehicle is doing that? Is the SQL as a vehicle. SQL as a vehicle. We had a SQL compiler compiled, and then after that, the SQL compiler is telling each component doing things. Here is the move programming. So, for example, the Libra transaction coming in, the validator is going to do that. Is going to do a transaction. Okay, your transaction is it has a transaction called state machine replication, and then after it's scaled that is going to the broadcasting to all the validator. Validator are doing the consensus. It coming back to the validator, and then this. And I think about that's an idea, right? Since Mu is a program language, but people are not used to it. But we are able to, can we come up with the SQL compiler? We can a SQL, after people are programming the business logic and SQL statement, and then we transfer into a Mu, a binary code. And then so that people are able to use, the developer are able to use the SQL statement to do the smart contract programming. That will be that will create a huge amount of the business opportunity, which means that your existing RDBMS logic, you don't need to change. You maintain the SQL statement, right? You can move. I mean that a subset of the SQL, right? Not need to be the Oracle SQL or T-SQL or something, right? A certain set. People are used to, are familiar with the SQL syntax. I use a customized SQL using is a Mu programming language. Mu is a programming language, a resource programming language. I'm not talking about that much about Mu, but the SQL we used to it. So that's an idea so that we can extend it. Later on, I'll talk about it here, right? That this one, right? When the transaction is a transaction log, right? Like Libra transaction coming in, there is a state machine replication is in the validator, and then come out with the new transaction. And then it's going to dump into the ledger history. Ledger history actually is a ledger database. Ledger database now is the LogDB. LogDB, we all know that is the key value. So the reason why my extension is that, right? We use, by this way, we just doing the SQL as a slave. We use the LibreDB as a master. We use our traditional SQL server as a slave so that we can provide a service to our application. Because the slave is not changing. Like they had a lot of complexity and the business, the movement already able to handle by this kind of things. So that we are able to become, improve the performance. So make sure the Libra database it become high performance, high availability, and high scalability, right? And also we are able to use the SQL as our programming language, as our smart contract. We maintain. That's why in my open framework, we call it Violas. Violas. That's why I'm doing not advertisement, right? But we really moving into this idea is that we're going, if possible, we have enough resource. We are going to make some SQL modification to make sure a Libra. Now Libra core is the proof of concept. There's no Libra enterprise yet. If we come up with a Libra enterprise database, then there will be huge amount of the business in the future. Yeah. So, so that's it. Yeah, I think I'm not sure if I have enough time. Yeah. Okay. So.
Yeah.
So before I go into the live demo, any question or anybody come up with anything?
Yeah, can you move to the last page actually?
Last page, right?
Last second page, yeah. For them, yeah, this is the left side, the previous, yeah. The left side, no, or this one, yeah, that's fine, yeah. So because whenever you, for example, you want to update something, and there are a bunch of these validators, right? And if everything goes smooth, then everybody will store the data, right? Then store the transaction, right?
Yeah.
So when can we think this transaction is successful? So that means all the participating nodes give a okay to the leader, and then the leader get back. But just in case, for example, if there are like 100 or 1,000 of the nodes, how this is possible? I mean, anybody can fail, right? And also it will take a very long time, right?
No, that's okay. So let's come up with in this here, right? Okay, it's a broadcasting right here. Like it's the broadcasting. Then they had the network is a broadcasting. Okay, okay, I know your concern, right? Here, right? Okay.
Yeah, I understand. It's a
this
peer,
one is broadcasting,
like,
right?
Yeah, I know. It's the like the gossip protocol, right?
Yes,
For example,
yes.
consensus is like a gossip. So, but still, I mean, all the involving nodes get the updated state. It will, and then they have to everybody has to get back to the leader. I think this process is very fragile. You know, it's very easy to break, as I see, because you know, at any place, if it breaks, then you know you cannot get back to the leader, right? Then
That's right. Good question. This is a good question. That's why you see that in case the leader fail, right? So anybody can be done, right?
Yeah,
anybody can be done, and then there's a timeout because the request is still in the memory of everybody. Right? If a leader is failed, and then they're going to and right here, right? So if it come up with a consensus, sending okay, leader is failed. Now we don't have leader, and then we come back to the memory pool, and then the consensus pick a leader, and then we go back to the memory pool and to do a consensus. We have to do a consensus that way. That's the reality. Otherwise, you cannot maintain the data integrity. How can you maintain integrity?
Yeah,
that's the most advanced algorithm now.
Yeah. Okay. So let me. So when the client want to make a request, so who does the client talk to? Because there's no leader, right? The leader is selected. Selected dynamically, right?
Okay, that's good question. Here, right? For example, you send as long you have the validator. For example, John sent. He had a request. He sent to the validator in New York, right? It's the New York. New York is not a leader. At least it's not a leader yet. New York just I collected the information because based on my local, because my local version of the data is universal. It's same as the other. And I verify you. Okay, you are in this chain. You are Alice, right? And you are able to manipulate your account and resources. And then I send. And I send to my memory. And my memory pool, you see here, I send to all the validator. I send all the validator. Now, we don't know who is the leader. Maybe a validator in the London is the leader. It doesn't matter. If a London leader is down, maybe the other Beijing leader is going to up, right? You understand what I mean? Toronto leader is going up. So it's randomly. So which means that in our RDBMS, we always know who is the master.
I know, but the thing is, the problem is the client, for example, the client talks to Toronto leader, for example.
Yeah, but not Toronto leader, Toronto validator. Okay,
talk to Toronto validator. And
it's the whole network design the leader. We don't know the leader. They vote for the leader.
Okay. Who is responsible to get back to the client? So
it's the leader. It's the leader. No. It's still the Toronto validator.
Validator. Okay.
Yeah,
okay.
Because the Toronto validator is going to, at the end of the consensus and the protocol, he has to be sync the data to his local. So to his local data will have Alice is $100 for all the sites, all the nodes. It's the same. That's why it's very important saying that it's one version database. Blockchain database is a one version database. Even the data is doing the consensus is a multiple copy. For example, Toronto copy is using its own copy. Instead of the master slave is only using the master copy. No. The London the validator using London's copy. They had a multiple copy, but at the end, the multiple copy of the transaction data has to come up with a consensus and dump it into his local single version data storage.
Okay. Another question. You talked many times about the consensus. So what kind of secret is the consensus on? So what kind of information they have to have a information which
here, right? The consensus is the database protocol. This slide, right?
Yeah. I know. I mean, what exactly the information they consensus on? For example, they get some.
No, the transaction. Okay, good question. Okay, called transaction state change. I change the state. For example, I want to change the state from the number Sn-1 to Sn. Are you agree with that?
how
If you
does
agree,
they know
you dump
no?
it into your local storage. If you are not agree, you will be able to sync from the after people vote.
Okay, so suppose I'm a node. So in this case, I will check my local copy.
Yes.
And the current balance is 110 and 52.
Yeah.
And then this part is we agree on this only on this part, right? And the number 10 pounds from this account to that account, this part is not there because nobody knows that, right? Only you know that.
Yeah,
right?
of course. And then you need to check, you need to go to the memory pool, right? To get your data, right? Your memory pool talk to the consensus saying that, okay, now you are state 100. The whole network, the state is already 103. You are the one actually not sync. You need to sync first before you can handle. You are the person behind the network.
Yeah, okay.
Okay, I have a question here based on the architecture diagram or some data flow and the validation or transaction law. This type of requirement is very complex. So, but the implementation, what implementation is there to ensure you can get reliability and high performance? Do you have a solid use case to show us how much transaction volume you can handle for this Libra chain?
No, it's a good
database?
question. So now Libra is not heavily tested yet. That's why it's just very beginning. So we are
there is validator in computational world, and nothing.
They had the benchmark. They had the testing. They had the benchmark. But I'm not sure that benchmark actually now really makes sense yet. In the Libra source code, right? They also had the benchmark, and then they had a benchmark so that you can you can test it. What kind of benchmark you are able to meet? Yeah.
Sure.
And now we don't know. We don't have it yet.
Yeah,
they are testing. They don't even use in the Google, the Facebook Pay yet, right? Facebook, they had a payment system. They are not using it yet. They established a new payment company called Navy, right? Navy, right? And NAV, right? And then they are testing, and now I think it's in California or something. They are not using it yet. And my team, right? Is also we also have the payment system, but we also have a payment system. We haven't had enough volume of people as tested yet. That's why the Chinese central bank they cannot use the Libra technology because one is not secure. The second one is that now they cannot handle that huge amount of the people. They have to come back to the traditional way. Now the Chinese central bank digital currency is the DB2 orient base, right? Underneath is still DB2. That's why I talk about is that you still need the RDBNS to do the data persistence. Right?
So I guess every logic component, no matter to validation or to transaction or what storage, whatever, should be a truly distributed system. Can be anywhere. So this validator can be in China, another validator can be in Canada, another can be in US.
That's
so how do you streamline and reduce the latency to synchronize, make this transaction or validation?
Okay, your good question. Here is you can come up with this the protocol, consensus protocol. They has as I mentioned, right? As I mentioned, they has where is it? Right? Latency come up with a timeout. For example, the leader you send out, if a leader is in New York, right? He sent out the request. You need to vote. The London one, maybe London or European sites or Asian side, Tokyo, Beijing. You need to come up with the vote now. If the Beijing vote is done, I don't wait for you. You are a failed validator. But as I mentioned, right, you need to have the legit number. Legit number of votes. For example, I need to collect the 5 votes and I become a legit. The leader no need to wait for the down node. The validator down is down. That's the key difference about this consensus compared to the DRDA, Oracle's TNS, or maybe whatever TSD, something. That's different. It's not 100% availability. It's called force tolerant. That's why at the very beginning, I highlighted the force tolerant over and over again.
But you cannot, yeah, fault tolerance is okay, but here is a latency, right? Let's say the first leader timeout, then you select the second one, but you cannot guarantee the second one also works, right? In this way, the latency could be very high if you keep trying.
Yeah, of course. That's one. For example, you Beijing, you are in the state 100. If the whole world is already in 105, you will become unavailable. Because when you everybody you try to seek, you didn't get enough. Legit, we call it QC, called colon certificate. You don't have enough colon certificate on your network, so that you are not able to handle the transaction. You have to make sure you are online. Before you are able to handle, you need to sync. For example, you need to sync back to the 105 state you are able to handle. Otherwise, if you cannot get enough votes. That's why I tell you, if you're down, you just down. If you come back online, you come back online again. The latency, you have to maintain it, the network.
Think about the volume of data you have in each node. So it will take a lot of time to sync between among them.
Not take a lot of time to sync. This is a data persistent. For example, you already in state number 100. We check your 100, your certification, your validation is legit. You just add that the other 1, 2, 3, 4, 5. You add that a delta, should be okay, right? But if your node is too old, right? You have to sync for example, you have to sync back from the beginning before you can become available.
It's not a full sync, it's just incremental sync, but still you still need enough data or enough delta to get to be the latest. In order to participate in the calculation.
Yes, that's why there's a component called direct or RPC or something. As long as you have that one, you get syncing the data from your neighbor nodes, right? For example, Beijing, you already 20 years later, right? And then you need come up with, okay, I want to lie again. And then you have to sync from the Tokyo or Hong Kong or whatever Singapore nodes, right?
Yeah. So other questions, this type of liberal database, can any cloud, such as public cloud, that have similar implementation or modify current database in some cloud, such as Finder or whatever, they can take your protocol and then maybe they can have better performance than you or the liberal database. Is it possible? Or
yes.
Or you migrating your high-level diagram architecture into the cloud?
No, as long as you are able to receive the protocol. You agree with the protocol, you are able to define your own. That's a good question. And underlying the implementation can be different. Can be different. That's why you can see that the Oracle database can talk to DB2 database, right? Because you have the database gateway. They talk to the same protocol, right? The Oracle has the DRDA gateway, right? They can talk to the mainframe, right? And that's why they can communicate. They can sync data. As long as you are, for example, this is implemented in Rust. You can implement in C++, but you have to maintain this Libra protocol. But now it's not yet, because you are in the binary level. You have to implement the what? You have to implement the admission control, memory pool, consensus, and really basically you have to implement the virtual machine. Because the virtual machine, they had a really, we call it close couple, right? The tight couple together is that your code need to be executed from the virtual machine. Otherwise, I don't trust you, even local. You understand what I mean, right? Otherwise, you hack it, and then you are the traitor. You hack your own virtual machine, and then you're saying that you become the fourth, you become the traitor general. right? But you need to have the virtual machine implement. I can recognize you. Otherwise, I kick you out of the protocol, right?
This solution or architecture still depend on or advantage or disadvantage or drawback of any distributed system, such as latency, network reliability, whatever. So your bottleneck is still there.
You mean the bottleneck about performance?
It's
right?
still network.
No, I don't think so. The future
Still
of the
network,
network,
still
I believe that this won't be a bottleneck. Won't be a bottleneck. You're thinking a huge amount of the data in the network. You don't need to cross the continents, right? For example, this system, how about all nodes are in Toronto, right? How, as I mentioned, how about all the nodes, all the bank nodes are all in the same data center in the same rack. RBC nodes are in the same rack of the TD. That's why. Now you understand what I mean, right? Why I come up with this one, right? Why? Because the green and orange, they're different, but they are in the same rack.
But based on definition, you say this is a truly distributed, no leader, no master, no single database. So location is transferred. So,
Yeah.
but now you say still the same, not truly distributed. So.
Oh, I understand. No. It's still distributed. There's no 100% distributed. We call it peer-to-peer, right? Actually, some of the peer-to-peer, they have to go down, right? Yeah. So that's why the database is still very new. I understand that. You always think about what our DB2 Oracle has, and then you compare to this one. But now there is achievement for that. Is that all the banks are using the same database. That's very true. For example, you can see that you always use the Bitcoin, right? The Bitcoin is everywhere. Now we don't know, just like previous, the cloud idea, right? People are saying that, oh, cloud is not safe. What the hell, I'm going to hosting my data in your location. Actually now, many of the organizations believe that the data hosting in the cloud is much more safer than the local.
Yeah, this is just some concept. In the whole world is the same data center. The whole world. Internet is a whole data center.
And then we always compromise with something, right? Yeah.
So regarding the state and transaction, is this state just one state for the full cluster? The question, the question, because if you didn't finish this transaction, you're still at state n-1. You cannot start another transaction.
Yes.
Right.
Yes.
So that's a throughput problem.
That's the validation thing. No, throughput is that only your nodes. The whole world, the throughput is still very fast. They're still able to maintain the local. For example, your Beijing nodes down. It doesn't matter. Toronto node is still up. The Toronto people.
No, I understand that. I understand that. Let's say you have a 10,000 cluster, 10,000 node cluster. They all at, state n-1, right? There's a transaction comes, so they all calculate that. That it doesn't necessarily to be all 10,000, but let's say half. But you have this transaction n is being calculated right now. Can anybody start transaction n+1?
No.
No, right? So you can at this moment you can only.
No, because the throughput is really quick. You need to check your state. Where your state, right?
I understand. Even you take 1 millisecond.
Yes.
Your maximum throughput will be 1,000 per second.
Yes, you need to check because the consensus is always there.
Hi guys, sorry.
No, if you want to do a no write, you just need to do a read. Should be okay.
Yeah, read should be okay.
Yeah, sorry to interrupt you guys, and we are running out of time. There's only 10 minutes left. So
sure.
It's a very good question, but let's have a
let's go to do a demo, right?
Yes,
let's see what is real the database is,
Yeah,
right?
yeah,
Okay.
Yeah,
So I'm going to
please.
do a demo right here.
Thank
right?
you. Thank you.
Okay. So here
Okay.
that we can get it from the the source. It's a GitHub. Then you can GitHub. You can have it. I think it's you can see that in the GitHub. Right, it's right here, right? All the source codes are here, right? And you can get it from here, right? And I got you can copy it, and I can have it in my local, and then you can see that, right? Yeah, not that many of the code, right? Compare DB2, TB2. When I was in DB2, it has a 2 gig of the source code. After I leave, DB2 has 10 gig of the source code. So now the Libra is still we call it tiny, right? The client, the common, conflict, consensus, crypto, right? And then the tool, they had a different tool. Execution here, RPC, language is they had the language, they had the compiler, right? They had the virtual machine, the move language. I'm not mentioning about that much about move language, just like SQL language is totally different, right? They had a nodes, a memory pool, and a network. Right? They all had not that many. It's all in Rust language, right? For example, we come out here, right? You got source code. Yeah, it's not that many. You see that it's a Libra node, right? Well, it's simple, and then you can launch it, right? And after that, you can just build. Right? I had the build here already. So here we are in a. So you can see that we have it, right? We just build it, cargo, right? Cargo build Libra. No, something. Yeah, we build it, right? So we build it, right? So and then we are able to run it, right? We are able to run it. For example, this is command line. Right? Hold on. I guess right here. This is command line, right? I run. I run a tested node, right? Cargo run local node. After you compile it, right? I'm not get involved with setting up the Rust language. After you have the Rust language, is cargo run. That's it. Just like our C is config and config make. And config made, and you're able to run it. It's a cargo run. Just run certain component. We call it component is that the Libra node. Yeah, we run it as a test node, right? Local. Okay, local here is that they had sending out a certain log file, right? And then here has the configuration. Configuration local. It has all the local the storage. Where is the key? Where's the data? Where is it? Everything, right? And the key is here. They had a key for authentication. They had a viewpoint. Viewpoint is an internal thing that you need to just like a navigation system. Like where is my location things? Here is the things. Okay. And then so we have use another client. I had a command here. I prepare some command. Command is running the client, CLI, right? We are running a Libra CLI. Libra CLI, where is it? Okay, here, right? Here, I got like Libra CLI. I will have a CLI running. No, I had to make the command, right? I had to make the command. Is that the command is here? Sorry about that. I need to change the key. The key is this one. Key, the private key here. I need to come up with it. And then the viewpoint. Okay, I run this command. It's just like a DB2 CLI things, right? And then here on the command. Okay, so we come up with the command line prompt. Right? The Libra 2 is me, right? Building, because I call it Libra 2, right? Different from the Libra. And then so that you can have the help. You can have help. This is command of the help. You can have I follow a command here. This is my simple command, command list, right? We call it account list, account list. So there's no account, right? No user account. It's a new, brand new, because it's going to use a local storage, right? And then I just do a account created, right? Account create, okay? This is the account create already. Number 0, account number 0. It has address. You say each account has address, and then all the resource is hosting, the move, your gas, your resources, your coin or whatever. Because now it's called resources. The programming language, and then how many resources you are binding to this account. So it's not the one, right? So we continue to create account called number 2, right? Number 1 account, they have different address. The address is the one. So account 0, we call it the Alice, right? Account 1, we call it the Bob. This is Alice and Bob, right? Then we cut, let's see, we cut account list. Okay. Oh no, here, account list. So you see that we had account, had the root or whatever information is already here, the number 1 or something, and then we killing the balance. So no balance, right? There's no balance here, right? And then number 1, no balance here. They don't have the balance, right? And then we mine the coin. Because it's local, right? We mine the coin. And then if in the real production 1, nobody are able to, it's the association distributed the mine, or I give you the permission to mine. They're going to deliver different component, the CLI, something like that, right? So that is demo local one, right? Because if you are hooking up into the global one, there's only one version. It's maintained by the Libra Association. It had by the Facebook. When they launch that, they put the money, the US dollar inside it. They are able to distribute that to you. So now we mine the coin called 110. Okay, it's mined that. The Alice had 110 coin. Now we call it check the balance. You see that the Alice balance is 110, right? And then we mine the coin for Bob. Bob is account and then called 52. Let me see, it's 52, right? 52 coin 1, right? Coin 1. You see that here is that now Libra is changed. Before it was only able to mine 1 coin. Now is that you are able to define your coin. For example, if this coin 1 is the RMB, that one coin 1 is the HKD. That will be system will become your system, right? The Hong Kong administration maintains its HKD, and each organization maintains its own coin. That's possible, right? The reason why is that you are able to use it in your system. So you can see that Bob is already mined, 52 coin. Let's check the balance of Bob, right? It has 52 coin. And then we'll see that the sequence, you can maintain a sequence 0, right? Sequence, visual sequence, right? The Alice is still in sequence number 0. Bob is also in the sequence number 0. And then we already had a balance, right? We do the transfer, right? Transfer is that very simple one. we transfer from account 0 to account 1 of the 10 coins, right? We're doing this command, right? Transfer, right? Accruing of the transfer already sent to the validator, whatever, right? Right? We can see that, right? Okay, now we can see the queuing the sequence. You can see that Alice's sequence number is already in number 1, which means that she already have a transaction initiated and sent to Bob, sent out. But the Bob's sequence is still number 0, which means that he hasn't do something yet, right? Which means that is not notified yet, right? And then after that, we are able to queuing. Let's check the balance. No, that's the old command. That's the old command. It's not here in new version anymore. See that? We can see that the Alice now is only had a 100 coin, and then Bob had a 62 coin. You see that? This whole complexity is here, right? We are already able to make a transaction. That's we can see that this is the Libra. And then based on the, we had a CLI. CLI is in the test suite. Yeah, CLI. CLI can be shipped separately, right? You can have this CLI command, just like you can talk to a validator. You can, as long as you maintain your key, right? As I mentioned that because every node, right? You want to join, you need to have the key and the viewpoint, and then so that you can join certain network. And then they had already also exposed the RPC API. If you are now is now is still no, now is the homogeneous it's just one Libra node by Facebook only. If they haven't exposed the different implementation using different organization that's using the same copy of all the data. Yes, I think that's the demo. I think we are on time. Yeah. So any question so far? Hello?
Yeah.
Yeah,
Thank you.
That's very simple, right? They call it Libra core is still the POC, but it's released already. Libra is going to use this one. They are heavily development. They already been tested with the many about the payment company. Right? Already some of the payment company already they already in tested. They're shipping their code to many of the financial institutions. They are heavily testing that. All the question and concern been sending out to Facebook, and then they collecting to the Libra team. Every day there are thousands of the commits online. It's very, very active, right? So that's why I think that this is the future. Yeah, it's very exciting to have the opportunity working in this kind of the future database. And there will be, and I can predict that within 5 or 10 years, all the bank, all the financial institution, you has to be in certain level of this kind of the database. Otherwise, you cannot be a financial institution because your fund is going to get it from this kind of database, right? Yeah, that's what I'm thinking. Yeah. Hello.
Okay, I think we run out of time. I thank you very much for Wenyan and give us this excellent presentation and demo. Yeah.
Oh, I see the question here, right? I have a
question.
We are only so the replica. Now,
let's discuss. You know, if you have more questions, let's discuss in the our online group. You know, we have Telegram.
Okay, every node has the right to write the
we have also
DB.
Google.
Yeah. Yeah.
Let's let's continue this discussion. This is a very interesting topic. I think we can continue discussion. I'm sure people after learn more, they will have more.
Yeah, because I don't have that much time. I'm fully focused in the code because learning the Rust language has a very long learning curve. Yeah, if anybody had interest, I can tell. But the Rust language is very advanced, and then I'm the C guy, right? Even not that many C++, but DB2 is written in C, right? So the Libra is in Rust, so I have to switch. Yeah, so languages shouldn't be a problem for us, right?
Okay.
Okay. Let's go back to the host.
Thank you.
Yeah.
Yeah. Thank you, guys.
Really, yeah.
Let's finish. We finished.
Yeah. Thank you. So I'll stop. Yeah. Okay.